From the beautiful North Studios of Way Happy, this is Mr. Meyer and 1-3 square roots. All right, what is a square root? So a square root, if you see these drawings on the screen, you see that that square, right, has a 25 units squared. That's the area of it. And a square root is, well, then how long is that side, right? So if I take a square and I want to figure out how long the side is, that's what it called a square root is. Now, some of them are easy, we know, because find area, you do this side times this side, and those two sides have to be the same. So what is their sides? Well, that would be right 5. I think 5 is the square root there, because 5 times 5 is 25. Do the same thing for 100. How long is this side? Let's call it x. And so if you wanted to do a little algebra, you'd be like, well, x times x is equal to 100. Most people would call that x squared equals 100. So what would x have to be? And I would say x would have to be 10, right? The side would have to be length 10 of the square. Now, sometimes we get hard ones, 75 square units. I don't know what that is. I can't think of anything. I know 8 times 8 is 64, and I know 9 times 9 is 81. So let me see, 8 times 8 is 64, 9 times 9 is 81. So let me think, it's somewhere between 8 and 9. It's almost dead in the middle. I mean, I'd call this about 8.5 or something like that. I think the actual answer is like 8.6 or something. I don't remember. But that's square roots. So that's how you find out each side. And square root is just figuring out how long that side is. Now, there are these perfect squares, like the 25, like the 100, and so you need to recognize a lot of them. And so let's talk about what they are. See if you can list them with me. I think 1's a perfect square, 1 times 1. What's 2 times 2? Well, that's 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8, 64. 9 times 9 is 81. 10 times 10 is 100. 11 times 11 is 121. 12 times 12, 144. 13 times 13 was like 169, right? And so on. I think the next one was 196. 14 times 14. And then 15 times 15 is 225. So there's a bunch. You want to know as many as you can. You want to recognize a number as a perfect square. So when I see 49, I'm like, whoa, I know that's 7 times 7. Or I see 121, I know it's 11 times 11. That makes your life a little easy. All right, let's talk about how we're going to use these. If you know them, just like you saw earlier, I can guess. I can estimate a square root, right? So 27, if I want to estimate that square root, I could be like, well, I know the square root of 25 is 5, and I know the square root of 36 then is 6. So it's somewhere between 5 and 6, and it's definitely closer to 5. So it's like 5.1, 5.2. You can see the book answer is 5.2, but I can tell right there that it's about 5.1-ish, right? Because it's definitely closer to the 5 than it was to the 6, because root 25 is closer to root 27, and it's pretty darn close. That's how you can estimate. That is very handy when it comes to solving problems. All right, what about this? There are different properties. There's called the product property, which says you can multiply square roots under the radical together, or you can have two square roots, you can multiply those together. Your choice, right? So as you see here, like 100 times a root 100 times a root 2, you could multiply that together to get root 200. Now that would be kind of weird because people like to reduce things, and the way we reduce is we break it down into perfect squares, then figure out what that square root is, and then leave whoever's not a perfect square under the radical. So you can see right here, I did 27 times 3, figured out it was 81, and then got 9. Division's cool too, because you could have a big old division problem. You can do the square roots individually, right? And then solve. Or sometimes it's nicer to take that division problem and actually just divide the stuff and then take the square root. So keep that in mind. Those are two beautiful techniques. You can either multiply first and then square root, or square root individually and then multiply, and the same thing with division. All right, so let's talk about example 2. I want to simplify these things, and I know the answers are there. I was just too lazy to cover them up. So what is the square root of 32 simplified down? So the way I do this is I just think of numbers that I know perfect squares, like like 4 and 9 and 16. 25, 36, darn, none of those. But I do know that this is 16 times 2. And then I know that that is root 16 times root 2. And I know what root 16 is. That's 4. So this is 4 roots of 2. And boom, there's your square root. Easy peasy, right? Now, another way you could do that, just so you know, is that I could go, all right, square root of 32. Some people will do what's called a factor tree, and they will factor this down as far as they can. So I'll be like, oh, that's 16 times 2, and 16 is 4 times 4, and 4 is 2 times 2, and 2 times 2. That's a great way also, right? If you cross out everything that you factored, now you can see I have 5 2's left over. So that's root 2 times root 2 times root 2 times root 2 times root 2. There's all 5 root 2's multiplied together. And then anyone you have a pair of, they become a real 2. So you can see that this is 2 times root 2, or what I would call 4 roots of 2. Same answer we got the other way, but just showing you another method to see if you like it. Some people really like the factor tree and then just grab things that you have a pair of. All right, what about B? B is the square root of 25 over 36. Now this is where you decide, is it easier to reduce 25, 36 right now? Or would it be easier to square root each one individually? And that's where you want to make sure you recognize things that are perfect squares. Like I'm like, oh, wait, those are both perfect squares, right? So I would much rather do it individually and then figure out the square root of 25 is 5 and the square root of 36 is 6 and jump up and down that I'm finished. So that's how they got the answer 5, 6. Let's look at C, which is root 3 times root 12. Now you got a couple of ways to do this. You could reduce it individually, which would work. You could multiply together and then reduce. So I'm going to do that. I'm going to multiply together, which is root 36. Oh my gosh. I know that one is just plain old 6. That was nice. But I could have definitely reduced individually and then gone from there. And last but not least, let's try D. You can, again, treat this as one big square root or treat them individually. Now, I don't know the square root of 5 or the square root of 500, so that makes me nervous. But I do know that if I put these together under one root, that would be the square root of 100. And I know that. That is 10. All right, let me ask you a question, and I'll be right back. All right, beautiful work there, and good job. Now we're going to talk about rationalizing the denominator. What does that mean? That means you got to do this math problem with all these square roots and you're reducing them, everything's good. You tried to reduce the numerator denominator stuff and it didn't work, right? In Algebra 2, we do not like to have what I call a hooker in the basement. See how it looks like a little hook? See how it looks like a basement? If you had a fraction, you have a top and a bottom, there's a basement. We don't like hookers in the basement, all right? So this is called, in math terms, is called rationalizing the denominator. And this is something we want to take care of. So it's quite simple. What you do is you make sure you reduce down as far as you can. And then whatever that is in the denominator, you multiply it. Because remember, you need 2 of those things in order to be a regular old number like we just had in the last examples. Root 2 times root 2 is a regular 2. And so what that does is when you multiply top and bottom by root 2, that creates a nice number 2 on the bottom. And the top, it makes a total mess out of, but we don't care, right? The rule is that we cannot have any hookers in the basement or rationalize the denominator. So that's the big trick there. All right, let us see what we can do then in the next one. Also there, by the way, you can see that when the next part they said you can combine like radical terms with adding or subtracting. Make sure that they're the same radical. I can't add them together here. But in this step down here where it was 3 root 2 plus 2 root 2's, that's how you get 5 roots of 2. Kind of think of them as x's, and you can only add them together if they are the same. All right, so here we go. We got a little bit of each. Example 3, I am going to simplify by rationalizing the denominator. So I come cruising over here, and we have 3 root 5 over root 2. You try to reduce that line. You're like, oh, 5 over 2, that doesn't reduce. So maybe I should make it a fraction, and that doesn't reduce. You could write this as 3 times 5 over 2, right? But that doesn't help you any because that 5 over 2 doesn't reduce. So you're like, ugh. So then there's really nothing you can do to this problem. It is simplified down as it can go, but we don't like that hookers in the basement, so we want to get it out of there. So I'm going to multiply it by a fancy 1. I'm going to multiply it by root 2 over root 2. Now why? Because root 2 times root 2 is going to be a regular old 2. And why is that legal? Because this is just like multiplying by 1. And you know, if you multiply by 1, it doesn't change the problem at all. And that's a good thing. So now I go over here and I go, all right, this is 3 times root 5 times root 2 is root 10. That doesn't reduce, but root 2 times root 2 is 2. I check to make sure the 3 and the 2 don't reduce. I'm not going to reduce the 10 and the 2 because one's under a radical and one's not. So life is good. I stop right there and I'm done. Nice? Nice. All right, what about this one here? B. If I'm going to do B, I got root 2 over root 8. Now I'm like, ooh, I can reduce that, right? I can make this 2/8, which means I can make that 1/4, which means I can make that the square root of 1 over the square root of 4, which is 1/2. And I jump up and down. That's one way. You could have also, the long way, rationalized the denominator by going root 2 over root 8. I could be like, all right, I got to multiply by root 8 over root 8. Right? Which would give me root 16 over 8 times 8. That's going to be a regular old 8. That would have worked too. And then what is, 16 we know is 4. So it's 4 over 8, which is 1/2. So no matter what, I would have got a half no matter which way I went. One way was maybe a little shorter, a little smaller numbers, but they both work very well. All right, and then adding and subtracting radicals. The rule is if they are like terms, you can add or subtract them. So here I see 9 root 3 plus 7 root 3. That's like saying 9 cows plus 7 cows. What would you have? Like I would have 6. Oh, go away, Cortana. I would have 16 cows. So root 3 was my cows, right? Now look at B. Say root 5 is cows and root 20 is chickens. What's 6 cows minus a chicken? Nothing, right? They're not the same. I can't do anything. Oh, wait, maybe I can. And they just didn't clean it up. So you're like, all right, I got 6 root 5 minus, now root 20, that's 5 times 4. So that's root 5 times root 4. Now I know root 4 is 2, so that's 6 root 5 minus 2 roots of 5. Look, they are both cows. 6 cows minus 2 cows is 4 cows. Or in this case, 4 root 5. Nice, right? All right, last one. Simplify that mess right there. Okay. So first thing I would do is be like, all right, this is 2 times 3 over 6, I notice would reduce to 2 root 1/2. Now remember, it's under the radical, so that's no good. I was hoping it would clean up, but it doesn't. So 2 root 1 over root 2, right? And then I would multiply, no hookers in the basement. I would multiply by root 2 over root 2. And what do I get? I get 2 roots of 2, because remember, I multiply the 2 with 1. There's a 1 out front of here. So outsides with outsides. And then I multiply insides with insides. So that's how I got 2 root 2 over. And then I have a root 2 times a root 2. Hey, that's sweet. That's just 2. Oh my gosh, the 2's out front will cancel. So that answer is just root 2. And there's many other ways to do that problem. That's just one way. Nice work. Now have a great day. Stay happy. And I'll see you tomorrow.